In this video, we're going to discuss solution stoichiometry. So we know that a solution is a homogeneous mixture prepared by dissolving a solute in a given solvent. So for example, we may dissolve an ionic compound in water in order to produce a solution. Many chemical reactions take place when we have two or more solutions that are mixed together. Solution stoichiometry is the calculation of relative quantities of reactants and products in chemical reactions involving solutions. So we take two solutions, mix them together, and they chemically react to form one or more new substances. Solution stoichiometry allows us to calculate such quantities as how much of a product could be produced from such a chemical reaction, or how much of one reactant is needed or used in the chemical reaction, which reactant is the limiting reactant, and many others. At the heart of every reaction and solution stoichiometry problem is the molar relationship given by the balanced chemical equation. So here we have a couple of solutions, potassium phosphate solution. Again, aqueous means we have the ionic compound potassium phosphate dissolved in water. So we have a solution of potassium phosphate dissolved in water, and we're going to mix that together with a magnesium chloride solution. These two will react, and the balanced chemical equation gives us the ratio. For every 2 moles of potassium phosphate that react, 3 moles of magnesium chloride will be used, 1 mole of magnesium phosphate will be produced, and that'll be a solid, and 6 moles of potassium chloride will be produced, again, dissolved in water. So keep this in mind. Anytime we have a reaction stoichiometry problem or solution stoichiometry problem, in order to determine or calculate the masses or volumes of products produced or reactants used, we must use these stoichiometric relationships given by our balanced chemical equation. Let's take a look at a problem involving solutions reacting together in order to help illustrate this. The problem says how many grams of magnesium phosphate can be formed when 35.7 milliliters of a 0.85 molar magnesium chloride solution is reacted with excess potassium phosphate solution. So we're taking these two solutions, reacting them together. We have 35.7 milliliters of magnesium chloride, and we have the molarity of that solution. And our potassium phosphate, we're told we have excess of that. Pause the video and give it a try and see if you can solve this problem before I go over it with you. Okay. So first, let's look at a general reaction flow chart for any reaction stoichiometry problem. So we have some known substance that we're starting with. We may be given the mass of that substance, the volume of that substance, or the number of atoms or molecules. Whatever we're given of our known substance, we must convert it into moles. With mass, we would use the molar mass. If we were given grams, we could use the molar mass. With liters, we could use the molarity to convert it to moles. If we were given atoms, we could use Avogadro's number. So when we have a chemical reaction taking place, whatever we're given, whatever we're starting with, convert it to moles using the appropriate conversion factor. Now, once we have it in moles, we want to figure out how many moles of our unknown substance, or the substance we're trying to find, we have. So here is where we always have to use our balanced chemical equation coefficients. So we take our moles of A, convert it to moles of B, using the balanced chemical equation ratio as our conversion factor. Then, once we have moles of B, we can convert it to mass using the molar mass of B, convert it to liters of B using the molarity of B, or we could convert it into atoms or molecules of B using Avogadro's number. So let's apply this strategy, or this overall strategy, to our equation. So in our problem, we were told that we had 35.7 milliliters of 0.85 molar magnesium chloride solution. So we were given the volume and molarity of our solution. This is our known. We're told we had excess potassium phosphate. How many grams of magnesium phosphate can we produce? Well, we're given the volume of our solution, and the molarity of that solution. So let's use let's convert our volume into moles using the molarity of A, in that case magnesium chloride. Then we can use our balanced chemical equation coefficients to convert it to moles of magnesium phosphate. That's what we're looking for. That would be our B. So 3 moles of magnesium chloride will produce 1 mole of magnesium phosphate. Once we have moles of magnesium phosphate, we're looking for grams, that's mass. So we use the molar mass of magnesium phosphate. So we go from volume to moles, moles of magnesium chloride to moles of magnesium phosphate, and moles of magnesium phosphate to grams of magnesium phosphate. So we can use this overall strategy to solve any stoichiometry problem. So let's apply that here. So we have 35.7 milliliters of magnesium chloride. I need to convert that into liters first. The reason for that is because the next step, I want to use the molarity of the magnesium chloride. Magnesium chloride, 0.850 molar, let's write that as moles per 1 liter. That way we can use stoichiometry or dimensional analysis to set this up. So remember, a 0.850 molar solution can be expressed as 0.850 moles per liter. And that's what we want to do. So that's why we have to convert it to liters. That way our liters cancel. We can calculate moles of magnesium chloride that we're starting with. Now we use our balanced chemical equation ratio. 3 moles of magnesium chloride will produce 1 mole of magnesium phosphate. And finally, use the molar mass of magnesium phosphate to convert the moles of magnesium phosphate into grams. Solve that, and we get 1.70 grams of magnesium phosphate. So that's the theoretical yield. If we have 100% yield, then our magnesium phosphate mass will be 1.70 grams. Let's try one more problem. How many milliliters of a 0.280 molar barium nitrate solution are required to completely react with 25 milliliters of 0.350 molar aluminum sulfate solution according to the equation below? Well, I haven't shown you the equation. Pause the video for just a minute and see if you can write the balanced chemical equation. This would be a double replacement reaction. See if you can write the equation. Pause the video. Okay. So here we have our balanced chemical equation. Now pause the video again the second time and see if you can solve for milliliters of barium nitrate needed. Pause the video and give it a try. Okay. So let's look at our strategy. In our problem, we're given the volume and molarity of aluminum sulfate. So we're given the volume over here and the molarity. So we can use that to convert it into moles of aluminum sulfate. Again, whatever we're given, convert it to moles. Next, we can use our balanced chemical equation coefficients. 1 mole of aluminum sulfate will react with 3 moles of barium nitrate. So use that ratio to convert aluminum sulfate moles into moles of barium nitrate. Now we're asked for milliliters of barium nitrate. That's a volume. So we can use the molarity of barium nitrate to convert our moles into liters, and then we can convert liters into milliliters. So here's our strategy. Start with the volume of aluminum sulfate, convert it to moles of aluminum sulfate using molarity. Then we take the moles of aluminum sulfate, convert it to moles of barium nitrate using the chemical equation ratio, and then moles of barium nitrate to liters of barium nitrate using molarity, and then convert that into milliliters. So let's apply that strategy. Starting with 25 milliliters, convert that to liters. Then we have our molarity. Again, we're using the molarity of aluminum sulfate. So please, when you write these problems, write out exactly which substance you're working with and all of your units. Don't try to take any shortcuts. It can confuse you. Again, we're writing our molarity, 0.350 molar aluminum sulfate, as 0.35 moles of aluminum sulfate per 1 liter. Again, write it all out. Now we can convert moles of aluminum sulfate to moles of barium nitrate using the balanced chemical equation ratio. And then finally, we can get our moles of barium nitrate into liters. Again, I've written the molarity of barium nitrate as 0.280 moles per liter. We can write it like this just fine. Now we're asked for milliliters, so then we can finally convert our liters into milliliters. And if we solve that, we get 93.8 milliliters of barium nitrate solution required to completely react with 25 mils of 0.35 molar aluminum sulfate. So that's our answer. So be sure you can apply that general strategy to any reaction or solution stoichiometry problem, and be sure you recognize when to do that. So practice some more of these. And again, be sure to write all of your units when you're solving these problems and use dimensional analysis. Don't ever take any shortcuts.